Good evening, dear students. Just because of some problem in my cell phone, I have to continue my previous lecture in two parts. First part I have discussed earlier, that is its second part, in which I have to I have to apply a Bernoulli's equation for consider section 1 and section 2 before orifice and after orifice. In that figure, we can easily see that is the area of orifice, that is denoted by AO, and that is A2 is the area of vena contacta, that is denoted by A2. That A2 is reducing area which having a relation between AO and A2. So A2 is equals to the product of coefficient of contraction into area of orifice that we discussed in the lecture. Okay, so when we apply a Bernoulli's equation for section 1 and 2, we get P1 by rho g plus V1 square by 2g plus Z1 equals to V2 P2 by rho g plus V2 square by 2g plus Z2. On taking a pressure head and datum head difference, we have P1 by rho g plus Z1 minus P2 by rho g plus Z2. That is the pressure head and datum head difference, which is equals to kinetic head difference B2 square by 2g minus V1 square by 2g. So pressure head and datum head difference is equals to the H, which we get from a U-tube differential manometer, okay, or from a Warden gauges or any dial gauges, okay. So that is equals to B2 square minus B1 square by 2g. On simplifying the above equation, we get the value of V2 square. How we get? On multiplying 2g with h, we get 2gh. On transferring a v1 square to the left hand side, so we get 2gh plus b1 square. That is equivalent to v2 square. So on taking a root to both sides, we get v2 equals to under root of 2gh plus v1 square. Okay, so in equation 1, we have two different velocity, v2 and v1. So we have to simplify that velocities. That's why we have to take some relation between area of orifice and area of vena contacta. So A2 is the area of vena contacta and AO is the area of orifice. So area of orifice is larger as compared to area of vena contacta. So how we can get the value of area of vena contacta? So we have to multiply a coefficient of contraction, that is denoted by Cc, and that Cc is always less than 1. So the value might be in points, in fractions. Okay, so then by continuity equation, we have q1 equals to q2. As we discussed about a continuity equation, we know that amount of mass flow per second through an inlet is always equals to the amount of mass flow through an outlet per second. So that is also known as volume per rate at inlet and volume per rate at outlet. So we know that its unit is meter cube per second. So on simplifying that particular unit, we can also write it as meter square into meter per second. As we know, meter square is a unit of area and meter per second is a unit of velocity. So what we get? If we put that relation in the cube, so we get q1 equals to a1 v1, q2 equals to a2 v2. So from this equation, we can easily find the value of v1. v1 equals to a2 by a1 into v2. When we put that v1 into then we put the value of a2 into that equation number third. So what we get? AO into cc upon a1 into v2. Then we put this equation in equation number 1 instead of v1 square. So what we will get? v2 equals to under root 2gh plus AO upon a1 cc whole square into v2 square. Now once again, if we taking a square to both sides, what we will get? We get v2 square equals to 2gh plus AO upon a1 into cc whole square into v2 square. When we take a same terms to same side, then what we get? V2 square minus AO upon A1 whole square into Cc square into V2 square equals to 2GH. When we take a common from it, what we get? V2 square is a common. Then the remaining term is 1 minus AO square upon A1 square into Cc square, which is equals to 2GH. Then on taking LCM, what we get? V2 square A1 square minus AO square upon A1 square into Cc square equals to 2GH. When we transmit that term to right hand side, what do we get? The value of V2 square. So V2 square equals to A1 square upon A1 square minus AO square into Cc square into under root into 2GH. On removing or taking root to both sides, what do we get? V2 equals to A1 upon under root of A1 square minus AO square into Cc into 2GH. So from the relation of rate of flow, we know that Q stands for A2 into V2. So when we put the value of V2 in equation number 4, we get A1 into A2 upon under root A1 square minus AO square into Cc into under root 2GH. So Q equals to A1 and the value of A2 is AO into Cc from the previous equation upon under root of A1 square minus AO square into Cc into under root 2GH. So the same terms can be cancelled from numerator and denominator. So the remaining expression is Q equals to A1 into AO upon A1 square minus AO square into 2GH. So that is the final expression for a theoretical discharge. So if we have to find actual discharge, then we can multiply a CD in it. CD is the coefficient of discharge. Okay guys, thank you very much. The further application I will discuss in my next lecture.